So section 2.2. So 2.2. You guys ask questions like number 1. So in number 1, I'm gonna show the image here. Kind of zoom in so we can have a look at it. So we're just gonna do all of them from number 1 just so we feel comfortable with this. So it says for the function g of f graph here, find the following limits or explain why they do not exist. So the very first one asks you, this blue function here is our g of x function, okay? So they're going to ask you limits for particular x values. So now when they ask you, like, what's the limit as x approaches 1, well, this 1 right here represents an x-axis, right? So the limit as x approaches 1, so I'm asking for this 1 right here. Does that make sense? That the limit says the x value because the x approaches that. Of this function right here, of the blue function. So as I approach 1, remember we have to approach from both sides, right? So as I approach from the left, what's the y value going to? 1. So it looks like this would be equal to 1, right? But as I go from the right, what's it going to? 0. For the limit to exist, they have to go to the same y value, right? But since the left goes to 1 and the right goes to 0, then the limit does not exist. So we'd say for 3a, we'd say does not exist. So let me write it down. So a would say the limit as x approaches 1 of g of x does not exist. Oops, you don't see it. Does that make sense? Okay. Now, for number 2, the letter B, it says, what about as x approaches 2 of that function? So as I approach 2, which is this number right here, this 2 on the x-axis, as I approach from the left, what's the y value going to? Okay, as I approach from the right, what's the y value going to? 1. So notice that since it's 1 in both directions, then the limit's going to be equal to 1. Is that clear? So we'd say the limit. So for part B, the limit as x approaches 2 of g of x is equal to 1 because it's the same number from both sides, right? How about for 3? So C says, what about the limit as x approaches 3? Well, as I approach 3, what's the y value tending to from the left? Where's it going to? How about from the right? Does it matter that this point doesn't exist there, that the evaluation is 1? Remember when I ask you about limit, I only care about what's the number when I get close, right? So when I get really close to 3, this y value is getting really close to 0, right? Same thing from the other direction. As I get really, really close to 3, the y value is getting really, really close to 0. So just because there's a hole there, it doesn't matter. Remember, the limit doesn't care about the evaluation. The limit only cares about close, right? Okay. What's that? The point doesn't matter at all, yeah? The point doesn't matter, no. So really what I'm only on the tracks. I'm only on the tracks. As I get really close to my destination, I'm getting really, really close to 0. Same thing out here. As I get really close to that destination, I'm getting really close to 0. Now, it's going to matter a little bit later when we talk about continuity. Like, you guys agree this function is not continuous at 3? The reason why it's not continuous at 3 is because the limit is equal to 0, but its evaluation is equal to 1, right? And for a function to be continuous, its limit and its evaluation have to be the same point. Notice how it's continuous at 2? I can draw this without lifting my pencil. That's because its limit is equal to 1 and its evaluation is equal to 1, right? Since the limit and the evaluation are identical, then that means it's continuous. It means you can draw that little spot without lifting your pencil. So it's not continuous here, but its limit is still 0, because remember, the limit only cares about close. So C says the limit as x approaches 3 of g of x is equal to 0. And then D, they ask for 2.5. So as I approach 2.5, well, I put a little mark here for 2.5. Do you guys see that little black mark? As I approach 2.5, you guys notice that it's approaching this little black mark over here? Now, since this is a line, since it's linear, the average of the x's is going to give you the average of the y's. Does that make sense? If this is in between 2 and 3, then this is going to be in between 0 and 1. So what's the limit as I approach from the left? Where's it going to? You guys agree that it's right here? Well, that's a half, right? How about from the right? Half as well. You guys agree? Okay, so the limit, so the last part would be the limit as x approaches 2.5 of g of x is equal to 1/2. I like fractions, okay? I want fractions more often than decimals, okay? But since they do have a decimal in the question, If you wrote 0.5, I'd be okay with it. Because if the question involves decimals, then you guys can give me decimal answers. If the question doesn't have any decimals in it, then I want rational numbers, okay? I want fractions. The reason why I force fractions is it makes you better at algebra. You know, you have to get like denominators, you have to combine, you know, it makes you better at algebra. All right, so number 21. Zoom it up. Okay, number 21. 21, we're asked to find these limits algebraically. So the limit as x approaches 5 of x minus 5 all over x squared minus 25. So a really straightforward kind of limit, which is totally going to be on a test, okay? You guys will have to do something just like this on a test. The polynomials will be different, maybe, but it's going to look a lot like that. So how do you do limits? What do I have to do to this g of x function? Well, usually this is called f of x, but we've had g of x in the previous location. But what do I do to this function so I can apply this limit? That's 23? Well, I'm doing it now. It's already written down, right? Okay, so I'll do 21 next. So you have to simplify this function, and you simplify the function through factoring. So this will be the limit as x approaches 5 of, well, the bottom is x minus 5, but the top factor is the x plus, the top is x minus 5, but the bottom is a difference of squares, so it factors in that, right? So then you cancel this x minus 5, so you're simplifying that expression. This is going to be the limit as x approaches 5. What's left on the top? 1. Good. And then x plus 5 on the bottom. Now notice I couldn't plug 5 in the original function, right? Because if you plug in 5, 5 squared is going to be 25 minus 25. I'd get over 0, right? So it's undefined there. Actually, remember what that means is this function has a hole at that spot. Does that make sense? Remember we saw holes before? It doesn't care that it has a hole. We only care about close, right? So when I go from here to here, this function no longer has a hole. But they have the same limit. So that means I can plug in 5 now, right? Because what's the bottom if you plug in 5 now? 10. Yeah, 1 over 5 plus 5, so this is 1 over 10. So we're done. All right, now let's ask the question. Let me do the question you guys asked. All right, 21 is, well, I need more room than this. 21 has radically. So 21. What about the limit as h approaches 0? Oh, this is a really good one. 3 all over the square root of 3h plus 1 plus 1. Okay, let me go back to this original function. The one we just did. Why can I not just plug 5 into there? Yeah, you're going to get 5 minus 5 all over 25 minus 25, so you're going to get 0 over 0, right? Remember, 0 over 0 represents a whole. Remember I told you guys that back in pre-calculus? So this represents a whole as opposed to an asymptote. So that means that's not right. Is that clear? That means that evaluation is incorrect. So I can't do it because we get the 0 on the bottom, right? Now I know you guys really want to, I know in your heart of hearts you really want to do the conjugate right now, don't you? Because what do you see in here? Why would I use conjugates? They're used to simplify what? Things with radicals, right? But before we start to simplify, what's the first thing we should check? Yeah, can I plug in 0 right now? Remember, I don't care that 0 is on the bottom. I care about if the entire bottom is 0 when we're done evaluating, right? So is this function defined at 0? Let's check. 3 all over the square root of 3 times 0 plus 1 plus 1. So this is going to be equal to 3 all over the square root of, well, that's just going to become 1 on the bottom, right? Under the radical. Square root of 1 plus 1. Oh, this is not 0 on the bottom, is it? So square root of 1 is 1, so this is 3 over 2. So we're done. This function is defined at 0, so no simplification needs to happen. I think in that entire section, I have to spill my coffee. I think in this entire section, all these functions are defined. They might be. Yeah, I think every one of them are defined at the value. So I think you just plug them in, all of them. So I don't think any of those have to be simplified. They're already been simplified is essentially kind of the idea. Does that make sense? What they've done is they've given you something that's already in the simplified form. They've kind of given you something that looks like this in a way. So they've already simplified, now you just have to plug it in. 30. Oh good, everybody's asked this. 31's a good one too. The limit as x approaches 1 of x to the minus 1. Alright, so when I do this function, can I plug in 1 right now? No. Okay, so it's not evaluated. That means I have to simplify, right? It's not defined at 1, so I have to simplify. What do you think the first step is? Conjugates are for radicals. Flip the x. Oh, x to the negative 1 is the same as what? Okay, so this is x approaches 1. So this thing right here can be rewritten as 1 over x. You guys agree?
Did you redefine that as x over x, or is that not necessary?
One more time, Alyssa. What do you mean?
Instead of having 1 over x minus 1, could you do 1 over x minus x over x?
Yes, we will. That'll be the next step. So absolutely. Yep, you're just ahead of me by 1. Noah, what's up?
When would you multiply it by x minus 1? Get rid of x minus 1 in the bottom so we can get rid of 1.
Well,
we already have a fraction, one fraction, so we have 2 fractions right now.
Well, when you see these fractions up top, you guys agree that I'm going to have to, really I'm going to have to simplify this numerator, right? So in order to simplify the numerator, what I want to do is eventually I want to do this division as kind of the goal here. So I have to, I can't divide with a binomial here. So what I want to do is I want to condense it to a single factor.
So you multiply by x.
Well, I have to get common denominators. I can't subtract these, right? Does that make sense? So what's the denominator have to be on this 1 so I can subtract these 2 terms? Okay, so that means I'm going to have to multiply by what over what?
X over x.
X over x. Is that clear? So now it'll be common denominators. So this is going to be the limit as x approaches 1 of 1 over x. This thing becomes x over x, right? When we're done multiplying that, and then this is all going to be x minus 1. All right. How do you subtract those?
Yeah, over x.
Yeah, because when you subtract or add fractions, the bottom is unchanged. Do you guys agree? The bottom stays the same. The operation happens in the numerator. So this is going to be 1 minus x, right? That's what's going to go on the top, all over x, 1 minus x, all over x. And I still have this divided by x minus 1. Can I do the division now? Can I do this division? How do you divide fractions? Because this is a fraction, right? The numerator is a fraction. Is the denominator a fraction?
Yeah, over 1.
Yeah, it's over 1, so it is a fraction, isn't it? That is a fraction, isn't it? So how do you divide fractions? How do you go one fraction divided by another fraction?
Flip the bottom one to multiply.
Yeah, I got to multiply by the reciprocal, so that's the denominator. You guys agree? So this is the one I'm going to have to flip. So this is going to be the limit as x approaches 1 of 1 minus x all over x. I'm going to multiply by the reciprocal of the denominator. So when I combine these terms, I want to these factors, I want to have a look what they look like. So this is going to be 1 minus x, and the bottom is going to be x times x minus 1, right? We're very, very, very close. Are these the same? Is 1 minus x and x minus 1 the same thing?
No.
No. Do they simplify? Here, they do. Let's just do a little work down here. So let me plug in numbers for x. Let's say x is 2. I'm gonna look at 1 over x all over x minus 1, but what if I evaluated at x equals 2? So this is going to be 1 minus 2 all over 2 minus 1, right? So the top is what? Negative
1.
All over,
1.
which is equal to?
Negative 1.
Okay, let's try a different number. Give me any number. 5, okay.
3.
1 minus 5 all over 5 minus 1. The top is? Bottom is? Which equals?
Negative 1.
Okay, give me another number.
3.
3. 1 minus 3, 3 minus 1. Negative 2 over 2, which is?
Negative 1.
What do you think this thing's going to simplify to? Okay, let me prove it though. So what I want to do is I want to make this 1 minus x look just like this x minus 1. The problem is their signs are wrong, right? This 1 is positive and this 1 is negative. This x is negative and this x is positive. So what can I pull out to make them the same sign? Okay, so I'm going to factor out a negative 1 on the numerator. Factor the negative 1 out makes this 1 what?
Negative.
And it makes this x.
Positive.
So I'm going to write them in the right order. The x is positive and the 1 is negative. You guys agree? Okay. I just wrote it in the same order so it looks the same as the bottom. But as long as the signs are good, you can change orders, right? As long as the signs are maintained. And now you can see when they cancel, you get this negative 1, don't you? So you're welcome to negative 1, right? You're welcome to do that. The x is still on the bottom. So this is going to be the limit as x approaches 1 of negative 1 over x, right? Can I plug in 1 now?
Yeah.
So this is 1 over negative 1 over 1, which is negative 1. That's my limit.
How would you multiply it? You multiply it by its reciprocal.
Okay, 47. What's the first thing we should check? Yeah, can we plug it in? Is this function defined at 0? Well, really, I'm kind of investigating the denominator, right? So, let's take a look. So if I plug this in, so let's try. Remember, a lot of times you can't plug it in. You guys agree? Because if you guys write 0 over 0 on a test and try to give me that as an answer, your points are also 0, okay? So, sorry, it's mean. So, I was trying to be funny, but didn't come out funny. It sounded more like a jerk. So, let's take a look at, you guys agree that I'm really investigating the denominator? Okay, so what's the cosine of 0? So we go over to 0, which is right here, right? And I ask for the cosine. The cosine, is it the x coordinate or the y coordinate? The x coordinate. So that's the cosine of 0, isn't it? Yeah, it is 1. So this is actually 3 times, well, the cosine of 0 is 1, isn't it? So this is 1 plus 0 plus sine of 0. I'll get to that in a second. 3 times 1. You guys agree? So we're good. I know I can plug it in, right? So let's find the rest of it. What's the sine of 0? Let's go back to 0. Well, this is 0. Sine is that one. So this is going to be 0. So that's 0 as well, right? So what we're going to get is 1 over 3. Is that clear? So since the function is defined at 0, you can just plug it in. 63. Squeeze theorem. Sandwich. So what it gives us is it says if the square root of 5 minus 2x squared is less than or equal to f of x, which is less than or equal to the square root of 5, what, plus x squared? 5 minus x squared. For all x where negative 1 is less than or equal to x, which is less than or equal to 1. It wants us to determine the limit as x approaches 0 of f of x. So what we know is I know that this function right here is sandwiched between these two functions, right? That it's above this function and it's always below this function, right? For these x values, right? In between negative 1 and 1. What can you tell me about x equals 0? Where does that live? In between this interval, right? So I know at x equals 0, this function is going to be bounded by these two things, right? It's going to be stuffed in between here. So what I'm going to do is I'm going to take the limit of everything. You guys agree that if I take the limit of this entire inequality, So let's take the limit. Take the limit. So that means, so therefore, the limit as x approaches 0 of this expression would be less than or equal to the limit as x approaches 0 of this function, which is going to be less than or equal to the limit as x approaches 0 of this function. Now let's make sure what we mean by limit, why I can do this. Now when we take the limit, I'm taking values that are very close to 0, right? From both the left and the right. Is that clear? So remember, this function's below it, so clearly I'm taking limits below 0, right? I guess, does that really matter? No, it doesn't matter. I'm taking, you guys agree that I'm taking numbers that are below 0 and above 0? Which of course lives in here. So these coordinates in here are going to be in this, so that means this is going to be below that, right? So I can essentially evaluate these functions at any numbers in between -1 and 1. I know that this is bounded. So since I'm taking numbers close to 0, it's going to live in here. Take a number close to 0, it's going to live in here. And numbers close to 0 is still going to live in here, right? So does it make sense I can take the limit of everything? Okay. What's the limit of this as x approaches 0?
Square root of
Why?
because you plug in 0 times anything with 0, and then 5 minus 0.
You guys agree that this function's defined at 0? Because you're not getting a 0 on the bottom, you're not getting negative radicals, right? It's in the domain. So this limit could just be found by plugging it in. 5 minus 2 times 0 squared would be less than or equal to the limit as x approaches 0 of f of x, which is going to be less than or equal to, well, this is going to be the square root of 5 minus 0 squared, right? So this is going to simplify to, this one's going to simplify to, and this is going to be, well, right, because it's going to be between it, right? So I know that root 5 is less than or equal to this limit as x approaches 0 of f of x, which is less than or equal to the square root of 5 as well, right? So that means this thing is bounded by root 5 and root 5, right? So that means this thing has to be what? Exactly. So therefore, this little triple dot means therefore, the limit as x approaches 0 of f of x has to be equal to root 5. So that's your answer.
I got a question.
Yes.
They call it theorem because the graph looks like a sandwich kind of.
Yeah, because the two functions are the pieces of bread and the other functions in the middle, right? Does that make sense? Yeah, they call it the squeeze theorem, the sandwich theorem, the I'm really hungry now theorem. You know, like. Any questions? I'll post this on the site. Well,
I have one question.
Go ahead, Noah, what's up?
3F. I decided to throw in a variable there, and my brain's like, what?
It's not a problem. Let's have a look. Okay, so this is the function. All right, so 3F says, which of the following statements of the function f of x graphed here are true and which are false? So for f, it says, the limit as x approaches c of f of x exists for every point c inside this interval. So let's just kind of double check what that means. It says that in between the interval -1 to 1, inside here, it says no matter what number I pick inside that interval, that the limit always exists. Now remember, it's open at -1 and open at 1, so it's not including the endpoints. Does that make sense? So let's just pick a point over here. What if I pick this point? Does the limit exist at that dot? Yeah, because from the left and the right, they're going to the same value, right? What if I pick a different dot? Does that limit exist?
Yes.
What if I pick this open circle?
Yes.
Yeah, because remember, it doesn't care about the point. It only cares about close, right? It's still going to 0 in both. How about over here?
Yep.
How about over here?
Yes.
How about here? So is it true? For every value in between this -1 and 1, there's always a limit, isn't there? Is that clear? Okay. It's a good question.